Welcome to my new calculus channel. My name is John Gabriel, and today I'll be discussing the very important topic of area with you once again, and giving you a bit of history and showing you how it led up to the new calculus integral. So let's begin. Now, I don't know if any of you recall, well, I suppose those of you who have been watching my videos will have seen several previous videos that discuss these concepts. But I'd like to once again remind you and bring them all together. So what was the earliest notion of area, do you think? Well, in the book of Elements, there is talk about a plane number, right? This is a number that was described by Euclid as being the area of a given rectangular plane. In other words, it was a product of the sides of a rectangular plane. And although it wasn't called area, that's obviously what was meant by a plane number. And similarly, the same thing is meant by a solid number, which is actually a product of three numbers, okay? And so the ancient Greeks didn't really formally define area, and they didn't even define the arithmetic mean, but I suppose they all knew what it was instinctively, since any given number is also an arithmetic mean, okay? So, and of course, if you study my article on LinkedIn, How We Got Numbers, you'll realize why that statement is true. Now, area can be thought of in many different ways. We could, for example, if we had a rectangle, I don't like that. Let's say we had a rectangle, like so, okay? And area doesn't necessarily have to be square units. It could be triangular units. So, for example, we could have a square divided into two, or we could even have rectangles. It could be in rectangular units, where we specify what the attributes are of the sides being multiplied. Okay, so you could also have that. And the worst case scenario is you could also have circular area. Okay, so it doesn't really matter how you choose to look at it. But is there a general way of defining area, volume, hypervolume, etc.? And the quick answer to that is yes. And I was the first to do that. And how did I actually come across that concept? Well, I have a very deep understanding of number, like no other academic before me has ever had. And I realized that immediately after the concept of number, the second most important concept in mathematics is the arithmetic mean. If it were not for the arithmetic mean, you would no doubt not be able to find areas under curves or volumes or hypervolumes, okay? You wouldn't be able to find them because an area is actually the product of two arithmetic means, and a volume the product of three arithmetic means. Now, I'd like to just basically go back to one of these cranks on the internet who talk about me and just show you that if you go to this page, you'll see how, for example, the hippie Dennis Muller doesn't understand what he reads. And so he tries to downplay the statement here. So he says, the average of a bunch of numbers is really hard to grasp. And you can read it for yourself, but you can see how he actually confirms everything I said about mainstream understanding. Okay. Now, I would never have realized these facts that, for example, the area is a product of two arithmetic means if I hadn't understood what is an arithmetic mean, okay? And in short, really, let's just quickly see what an arithmetic mean is. If I have, for example, 3 values, let's take these 3 values, like so, okay? And I decide to make these piles equal. I can do it by chopping this pile off and putting it over here, right? And then I'll know that 2 is the arithmetic mean of these 3 piles. Now you can think of these 3 piles as ordinates in a curve, right? Like that, 1, 2, 3. If I had to make them all equal, then that length, where they're all equal, is the arithmetic mean, isn't it? In other words, I make them equal through redistribution. I cut some of this off and I put it on the other shorter ones and so on until they're all the same height. That, by the way, is what enables me to find areas like this. And you too, incidentally, although you've never realized it. But the fundamental theorem of calculus, which is derived in one step from the mean value theorem, does exactly what I'm telling you here. It rectangulizes this irregular area or an irregular volume, okay? It cubi, I guess there is a word for it, but it kind of makes it into a cube so that the area, so that the volume can be calculated, okay? So it takes an irregular area, irregular solid volume, and transforms it into a cube, which is really the product of 3 arithmetic means. And this is, in fact, also what happens when you see things like the vector cross product in the surface integral, things like this. What is happening there is that you're taking the arithmetic mean of the normals to the surface, okay? And it still turns out that this here is also a product of 3 arithmetic means. Now, if you haven't done advanced calculus, you won't know what I'm talking about here, but that's not important. It works for any area and any volume. And I was the first to discover that. Now, that led to the new calculus definition of integral, which is available in this abstract. So if you go to the URL on my Google Drive, you can read the single variable integration and see what this is all about, okay? And I show you how I came onto it. I give you some historical background, and eventually I get to the definition, which is found on page 12. So on page 12, I show you how to find the arithmetic mean. And this here is not the same as x. And of course, if you watched a previous video of mine called Deriving the Arc Length, you'll know what that means. But inside here, this document explains all these concepts and how I arrive at the mean, at the formula for the integral, the new calculus integral, in a very simple way. And finally, I show you how from the mean value theorem, this here on the right-hand side is the new calculus integral. It doesn't use ill-formed concepts such as limits, infinity, and infinitesimals. And this integral is calculated in a fixed number of steps because it's based on the mean value theorem, which is the arithmetic mean of a given set of ordinates, okay? And when you have a double or a triple integral, the same thing is happening all over again. Okay, so that's the first part. Now, if you just bear with me, I want to show you something here on this applet. So, for example, if you're calculating the area under this curve, okay, this curve here, you can understand that new calculus formula because it calculates the mean. It works on the mean. So let me show you these ordinates. So these here are the means between these 2 points and these 2 points. And if I had to draw a red line there, that would be the mean of the whole interval, okay? And all I'd have to do is just multiply the length of that red line by the length of the interval, or this yellow line, to get the area. All right, so the area is that. And this is really, if I show the primitive function, this is how the area is calculated. And it doesn't matter how many number of intervals you have, 1, 2, 3, 4. This red line here is always the arithmetic mean. And these blue lines are the arithmetic means of these intervals, okay? And so you always end up with the same result. And this works for any function, doesn't matter what it is. Now, bear in mind that if you're calculating areas, they must either all be above the curve or below the curve. If you mix the two, you will get an integral value which doesn't mean anything, because the ordinates underneath the x-axis are negative. So you'll get an arithmetic mean which isn't really representative of the area given in any respect, whether it's the collective areas or the single area. And it's not the net change, because that's just a load of hokey pokey, okay? That's just nonsense. There is only one fundamental theorem of calculus, and it's got zero to do with change. Now, that's basically it. If you have any questions, you're welcome to post it in the comment section of this video. Hope you've enjoyed this little presentation, and that you'll join me again in the future for some more interesting details. I will try to expand and expound on this as much as I can. And by the way, I'm writing a new book, which is going to be an introduction to the single variable new calculus. So I hope to finish it someday, and if I do, it will probably be distributed as an ebook, and you should be able to teach yourself calculus, the new calculus, from it in a very short space of time if you're a high school graduate or if you've already learned calculus. So that's pretty much it. Okay, this is the New Calculus channel. My name is John Gabriel. Until next time, goodbye.